and it also operates leadership computing facility. And our next machine will be based on ARM chips, actually, on Fujitsu A64FX. And personally, I sort of do both HPC and AI, like natural language processing models, etc.
Welcome. Looking forward to that. Brent.
And I'm Brent Gorda. I'm Senior Director for High Performance Computing at ARM. Effectively, I own the HPC business worldwide at ARM, which is a bit of a new role. It's been historically operated out of the research program. I've got a rather long history in high performance computing going back to the mid-'80s, so I've been around for a while.
Great. Well, I've got some questions to start, but as this is a conversation, I urge you to think about your questions, bring them forward. There will be someone with a mic that can bring a mic to you, but I'll get things started for now. So let me see. Brent, let me ask you first. What data center workloads do you value in a supercomputer environment, and why, or do your customers value?
What data center workloads? So we mentioned this a little bit outside. I want to differentiate the workloads that you consider to be data center, which I consider perhaps Oracle databases or cloud workloads on HPC architectures versus the other way around. So I think one interesting data point that came up just recently is the NVIDIA acquisition of Mellanox. If you go and listen to the press Q&A session of that, the morning that it happened, Jensen says the reason that we acquired Mellanox is because we envision data center workloads in the future all running the same application and communicating in a low latency, high bandwidth environment. That to me was super curious. I'd love to have his answer as to what he's talking about, because that to me sounds like a traditional HPC application, low latency, high bandwidth, right? That's not generally the workloads that you see there. But so pop the stack, I think the data center workloads that you're going to see initially taking advantage of HPC architectures, the way we generally talk about them, are the deep learning systems, right? The ones that need to have a whole lot of flops applied to wide problems with big data.
Good. Alexander, would you like to add something?
I would say indeed deep learning is the straight answer, and other than that, you should just look at what is the difference between a typical data center architecture, right, and HPC. Both have lots of CPUs, both have lots of GPUs. The differences in connectivity and a bit in software infrastructure. So clearly, we don't see mobile game backends running on HPC, and those workloads which are becoming. I wouldn't say it's the workloads that migrate to HPC. That's workloads that are changing in nature. Like deep learning is getting bigger. People starting training on a larger scale, and so, like, to accommodate this, both things happen. It's either workloads migrate on more appropriate environments, or environments become more appropriate. Like we see more and more, cloud settings introduce tightly connected islands, InfiniBand connected racks, etc.
So we're seeing the convergence of
yeah,
the hardware architectures.
It's coming from both ends. It just the hardware adapts to the demands of the workloads.
It should.
Okay.
It doesn't always.
So what do you think, Andrew?
So we have a long history of doing simulation. This is essentially bulk synchronous parallel workloads, categorized by MPI. But it's quickly become the situation where that alone is not enough to complete some of the work that we have. It's more than just simulation. It's about encompassing that simulation with a wider workflow and ensemble. This could be machine learning tools or data analytics tools to do in situ analysis of your simulation in real time to detect maybe a bad run or an anomalous event in your simulation before you spend the next 12 hours continuing that computation. There's a lot more that goes into this than just simply running an MPI, bulk synchronous parallel workload. And we're seeing that expand and grow substantially.
So are we seeing also then taking the traditional MPI and other workloads that are in HPC and supercomputers and driving those down into traditional ARM servers that we're building these supercomputers from?
So I think the answer there is yes. And the story that I want to bring up comes from, I don't know, 11, 12 years ago. I started this event called the Student Cluster Competition at SC in SC07, I think. And I was looking around for data sets that I could use for these students to compete on. They were going to build a small cluster on the show floor and run some sort of science applications. I'm a cyclist, and so I immediately thought, I'm going to call up Trek, and I'm going to ask them, what do they do? Because Lance Armstrong was big at the time. They were putting him in a wind tunnel. And I wanted to ask them, do you do any sort of CFD simulations on your frames? And I did manage to get to the developers at Trek. And they said, I told them about the event, and the first thing they said is, can we get the resumes of these students? Because we would really like to have the capability to do CFD design on our bicycles, but we're scared. We don't think that we know how to run a cluster. We don't think we know how to run an HPC environment. Right, that was 07, so 12 years ago. Fast forward to today, it's all over the place. They're doing that. The people who design pipes are running these CFD applications. Us old timers think of that as a bulk synchronous, I don't mean to call you an old timer, I'm pointing at myself, but we think of that as a simulation application in a bulk synchronous kind of manner, but the end user is just presented with a better interface than we've grown up with command lines, and they get to specify their widget and put it into the environment they want and develop a better widget. And so when we hear about HPC moving out into industry, those are the sorts of stories that come to mind to me.
Yeah. Very good points. Are there any problems that we need to solve as a community for data center workloads to truly be or successfully be adopted by the supercomputers? Let's say, Andrew?
Yeah, I'm going to quickly point out the software ecosystem, right? The tools we use to run our MPI workloads are totally different than what the rest of the world uses. And that's a good thing and a bad thing. That's sort of a characteristic of the type of workloads, right? Historically, a lot of the data center workloads are about doing, a whole bunch of things concurrently, but that's processing, web requests versus we're taking one problem and decomposing it into itty-bitty little pieces and doing those in parallel. I think we're starting to see a convergence of that with a lot of the deep learning frameworks, but there's still a lot more work that we need to do in the software ecosystem to sort of blend those environments together. MPI is not always very fun to work with, and if you can abstract that or maybe leverage the same tools that MPI has been, taking advantage of for the past decade or two, I think there's a lot of value there.
Okay, do you want to go next?
I agree. It's all about software ecosystem and not just an abstracting, API, but just very basic user experience. Like you launch a job on supercomputer, you go log into the terminal. There is a black window. You type, whatever your scheduler you're using, Slurm PBS. But in Amazon, you have very nice command line interface. You just from your laptop, you spin up 10 instances and launch whatever MapReduce job you're doing on the cloud. So that's what we want to see on HPC, and it's slowly moving in that direction.
So I think the Achilles heel for HPC is our lack of resilience. Our programming model is such that if anything breaks at any time, the whole world comes crashing down. I created a company based on that and sold it to Intel because the defensive I/O you need to do, right? These jobs run for months, and if it's going to crash once a week, you're not going to make any forward progress. So you have to have a considerable amount of defensive I/O to be able to save state and be able to restore it after that machine crashes. In the model of data center, take Amazon for example. If you think about Amazon as just selling books, when something crashes there, somebody buying a book goes, oops, I got to restart and try buying that book again. In our world with simulation, the whole world comes down and you lose all the work up to date or all the work from your last checkpoint. That to me is a serious Achilles heel, especially at scale where it matters more.
Yep. Very good points.
I'd also add the other sort of problematic point with HPC is the fact that we still treat everything like a batch. Life is a batch in HPC.
True.
For lack of a better saying. But we see in the cloud world and a lot of throughout industry, there's a lot more flexibility that can be had with your computation. And I think the more we can, blend those two ecosystems and sort of that user perspective and experience, I think the better off both systems,
Right.
both ecosystems will be. Right?
This is sort of where I was going yesterday with my talk about HPC and the fog, right? You're moving the workloads that we consider to be HPC, yes, they're MPI, yes, they're bulk synchronous, further out towards the edge where response time is much more important, right? Human response times are measured in seconds, right? There's kind of 3 levels of that, but they're measured in seconds, and you can get that kind of response in that environment by putting sufficient resources out at the edge. I think that would be a positive direction to go.
Good.
We need more questions. We need more questions.
More questions. So are there any questions now from the audience for now?
You guys can't be this nice.
It's too early. I heard there was a lot of drinking last night. Every night.
Over there, Carl?
Here. Here's the mic.
Thank you. So, Andrew, in your talk yesterday, you were describing some of the problems that you're having, which are a lot of the problems that we have in the commercial space of dealing with large fleets of machines, trying to understand what's happening with them in terms of power, temperature, all of that fun stuff. Is there a way that the commercial world can better interact with the HPC world? Because we're solving the same problems. It would be great to be able to work together on that. And I'd love to know your takes on how we could do that.
I agree. Yeah, we probably do solve the same problems in very different ways. I have not seen a whole lot of open source projects on sort of the RAS daemons that people use, the way the metrics are pulled together, and how, say, Amazon manages their data center, for instance. That's all proprietary as far as I can tell. I'd like to find a nice open source project where we can sort of share in that space. And standards. Again, if there's a set of APIs that we can all agree on, whether that's Redfish or some other way to sort of harness some of the metrics that we're getting from individual components of these large systems, whether it's a supercomputer or a data center, and figuring out nice, ways that we can use the same tools to harness and sort of process that data, know, when my random one node out of 10,000 went out to lunch and why, right? So. That's I'd like to work in the open source sort of arena in that space, and I don't see a whole lot. There's some generic tools, but I think there's a whole lot more work that's being done, both in HPC and in this industry, that we should be collaborating on.
I'd like to point out, I've worked both in the public sector at the DOE labs for quite a while, as well as in the private sector, and the answer you just heard to me was, at the labs, we're willing to work with you on any problems that we share, and we're willing to make them open source. We're willing to fund them to a large degree, and we're willing to be the first beta test user of that sort of thing, so you don't have to put your production infrastructure at risk on this new software. The labs are really good at partnering like that. That's why yesterday I said HPC is a great community to do upstart things with. If you can bring problems to the folks at the labs that you care about, they're likely to be able to either team with you directly or point you at another lab that is investigating that sort of thing. It's very open and engaging.
Yeah, we're happy to live on the bleeding edge and have been doing so for a while, right?
Absolutely. I would certainly say that with achieving the first ARM-based supercomputer in the top 500 list. It's a great achievement. It also points out that you also built the first Petascale ARM-based supercomputer. So what's it going to take to get past Petascale to build the very first exascale computer? So Alexander, I think you have plans for one.
In a sense, the machines that we are building will be exascale. It will not be exaflop in terms of FP64 precision, but it will be near exaflop in terms of application performance. And anyway, even in terms of lean pack flops, it's just a bit away from that mark. So I don't think there will be any fundamental challenge to just doubling it up eventually. But yeah, we've been saying all times that this lean pack marks are not that sensible anymore. there are many players who just game those cores with application performance suffering essentially for the sake of building stunt machines, and we are not interested in that. And yeah.
To try to add to that, the DOE specifically defines exascale as producing systems that are 50 times faster than what we had in basically 2012 to 2014. So, Titan and Sequoia, the couple petaflop range. That does not mean the same thing as hitting exactly 10 to the 18th floating point operations per second, right? I don't actually care, and I don't think anybody who's actually doing good science cares about hitting that true exaflop number. It's more about enabling our codes and enabling the science that we're doing at a whole new scale and capability than we've had before. That's what exascale is about. So whether that shows up as 1 exaflop or 2 exaflops or a quarter exaflop, I don't think it matters. It's about the science getting done. And that's a lot of what we were trying to do with Astra is, we weren't going all the way to exascale, but we wanted to sort of, try to identify what the path was for this sort of architecture. How do we get there? We got to start with Petascale. So.
That's right.
Gets too political to add to that answer.
Sorry.
No, that's fine. There's two buckets, right? There's the buckets of scientists that care about the performance, and then there's the bucket of politicians that care about having that marquee on their country of hitting exascale.
LIMPAC looks really good on, your one-line statement to Congress or in the New York Times, but
yep.
Yeah.
So I have an easy question. What does HPC look like in 10 years?
Ooh.
Good one.
Interesting. I think the pendulum, do I get to take the risk and go first? I think the pendulum that I see is swinging back. We've had 10 years of attached processors, and we know that they're difficult to deal with. When you see the Fujitsu architecture, you realize that a standard CPU is now becoming as capable as a GPU, and the architectures are going to converge. But with the slowing down of Moore's law and Dennard scaling, I think what you're going to see more are chiplets where you've got architecturally specific silicon embedded in a chip, so that, for example, if you're doing AI, you can have your AI algorithms not in an FPGA but in silicon next to your standard processors. And so the 10-year time is really interesting because I spent a bunch of time studying quantum computing and almost went to work at 3 different quantum companies, but none of them could answer the question whether they would have a viable product before my kid graduates high school in 10 years, which is when I would consider being out of the market. So you're right on the edge of where a quantum computer may exist, and to educate everybody here and show my prejudice, if it does exist, it will be an attached processor. It won't be a standalone system that does general purpose computing by itself.
Yeah, I generally agree with that. I'll say the same thing in a slightly different way, and that is the best answer I've heard for sort of post-exascale, whether that's 5 to 10 years or somewhere in between, is heterogeneity and embracing heterogeneity. And I don't mean putting a GPU on all your compute nodes and, hey, look, I have a heterogeneous system. No, I mean more the extrapolation of that concept to an extreme level. Not building a system or building a system that has maybe multiple different attached chiplets or accelerators or some non-von Neumann system attached to my traditional CPU, but also having a very diverse set of those across the machine, right? Right now, all of our supercomputers that we buy are essentially the same, right? Just take a node architecture and multiply that by 10, 20,000, right? I don't think that's going to be the reality post-exascale. I think we're going to see really diverse and heterogeneous systems, both intra-node and computing resource. And that's going to be really tough to harness.
Where's the fine line between a single system that you described like that and 2 systems? One made up of this architecture, one made up of that architecture.
Good
Perhaps
question.
on the same.
I think the unifying aspect is going to be I/O, whether that's interconnect or storage, right? Because at the end of the day, I'm going to have one workflow ensemble that's not just my simulation. It's maybe 20 simulations along with, you know, a data analytics component, a visualization component, et cetera, and they're all going to use their own little specialized bits of that hardware.
Still with Buster?
So it's still we're still gonna treat it as one machine, I think, because it's gonna solve one or two or a small subset of very big problems.
Is it still going to be Luster?
Please no.
I agree that the slowdown of Moore's law will be a driver. How exactly will it manifest itself? Some emergent architecture probably will be under more pressure to not maintain the sort of backward compatibility and use same architecture. I'm not sure if it will manifest itself as heterogeneity or just entirely, you know, new incompatible architectures. But it's one of those two, I'd say.
So this is the ARM business model here is completely critical, right? You can't take an x86 core design and build your own thing around it. You're not going to get to license the x86 ISA. Right here is ARM's opportunity at the server side to make a big entrance by licensing to Fujitsu, who can then take and add their own amount of I/O, special sauce, HBM, all that sort of stuff. Right now, computer architecture is very sexy again, and it's going to be for the next 5 years. That's going to balloon up, and in 10 years, you're going to see it filter back down to the important architectures that are mainstream at that point. I hope that ARM is one of the more important ones in there. Obviously, the x86 market is going to react as best they can, and the RISC market is going to try to catch up as well and try to do their thing. So I think it's a really cool time to be doing computer architecture again.
Very good point. The diversity of the ARM ecosystem is based on having a robust instruction set that allows these custom cores and custom architectural designs to really create these massive supercomputers possible.
And the advantage is that the software runs everywhere,
yes.
Right? Because it's the same ISA, whatever somebody builds is going to run the base software. You may have to go through and do some optimizations, but at least you're running. Satoshi said, my machine will boot Windows. I don't know why you would want to do that, but it is an interesting statement that it can do that.
And that's a big underpinning of the convergence we're seeing.
Yeah.
So we are close to wrapping up. Do we have any more questions from the audience?
Oh, there we go.
In the back.
This is kind of sideways, but with these giant HPC centers getting orders of magnitude better, is there a use for last generations now a tenth the size, so you can actually fit it into a building the size of a house instead of the size of a standard office building?
You could argue you see that already just buying a multi-core or many-core CPU, right? That was the reality a decade ago with supercomputers. So there is some scaling down or small, or leveraging sort of the economies of scale. But I don't think my supercomputer that's 5 years old is going to be useful for something else. I think the power to flops ratio is going to be cost prohibitive eventually, especially as we talk about pumping down, machines that are 10 to 50 megawatts, right?
I was thinking more of using today's or tomorrow's technology to solve the smaller problems that we were solving 10 years ago with a much smaller and cheaper computer.
Yeah.
I'm not sure I quite answered the question. Is it about a used market or about running
about a
software?
new market for,
Okay.
call it a medium performance computer, not a high performance computer, solving a problem like CFT
Right.
for a bike frame.
Okay, so this is a bit of a hobby horse for me because I've been in HPC so long and everybody talks about how small the HPC market is. It's restrictive, and the way to the story here is if you take a look at the European Processor Initiative, I mentioned it a bit yesterday, they're building a supercomputer capable of an exascale with an ARM-based processor and a RISC-V accelerator. The way they justify that project On a technical and financial scale, take politics out, on a technical and financial scale, is that one of those compute nodes is going to be what they sell to BMW to put into a car. And so the single compute node is a fully capable system, rewired for I/O and resiliency and so on. But you should see, if they're successful, you should see that same technology scale all the way down to one node and be available to the market.
So to try to add to that analogy real quick, we like to think of HPC as Formula One, right? We're going to an extreme here. We're going to try to get around this track as fast as possible. And hope is along the way you develop some technology that becomes applicable, say, to the Ferrari that you can then go buy a couple years later, and then another decade later in my, Toyota, 4Runner that I have now, right? So I think some of that trickle down happens, and we want to encourage that, but you really got to go compete at the extreme first.
It's happening right now internally where we talk about the SVE instruction as an HPC inspired capability in the ARM architecture, and we're seeing it being coveted by other workloads, and we're seeing it work its way down the performance stack into different IP that is available. So I have no inside knowledge, but I would expect that you might get SVE in your cell phone in a certain number of years, and that for image processing and audio processing, it's going to fly, right? And for AI, especially the recognition piece of that it's going to do wonderful because of that AI or that HPC-inspired feature.
I'd say the dirty secret of HPC is that most of the workloads you're running on these large machines don't run on the scale of the whole machine. And they could have quite comfortably be running on a smaller one. So there are applications which require full systems, and the full systems are needed to push forward the technologies, just been said. But if you look at any purpose-built system, for example, just any meteorological center, they just buy the scaled-down machine from Cray that they built, the big one for National Lab, then they sell a small one for whatever agency. It's exactly what's happening right now.
We're getting the hook.
Okay.
They brought the heat up here.
Yeah, I think you are. We're out of time. But it's fascinating. We'd like to thank you for
Thank you.
great yourself. Yeah, thank you.